Hello, in this tutorial I want to talk about modelling skulls and how best to apply boundary conditions. I've loaded a skull of a wombat here just for comparison. I'm going to be using a fox skull later on, and that's the one that's in the tutorial bundle. But this skull, although it has this strange artifact here, it's quite interesting because it just has a very different shape, and it helps to illustrate something else about the nature of the skull and how to apply loads, which is in the way that this ridge forms. So what we're going to be showing is how to do muscle wrapping and apply that to a skull. So we're going to be constraining our skull using the teeth, but just for the sake of exercise, I want to show what this muscle wrapping can kind of do into this interesting shape of this skull. So if I select some points just across that ridge, and that would be the normal way to do it with selecting boundary conditions, but that's no good. So we want to use this hand-drawn region here, this will just overwrite the previous selection. So if I just select this region by drawing around it, it selected those points there, and it can lead to some interesting problems, the selection itself. And if I then click extract and apply, we'll then get to see what that extraction actually looks like, and you can see that it's kind of quite ridged, so it's probably missed some points, which may cause some problems. But I want to, because this is just an exercise in what this kind of thing can do and what it's about, I'll apply the muscle wrapping, which is this button here on the VOX-FE tool set. And the idea is that we would set a force. I'm not going to bother with that part because as I say, it's just a sort of illustration, this. And I happen to know most of these parameters are actually okay, but I happen to know that the voxel size here is about 0.3. So we want to use a setting here for this point search radius of about 1.5, so 5 times the voxel size. Maybe even 1.6 would be better. And there's a target point somewhere sort of down here near this tooth. I'm going to set this to 105, 26 and 80, and for this parameter I happen to know, I'll explain a bit later, that 0.84 is kind of reasonable. So if I apply this wrapping filter, okay, it's going to present this sort of slightly strange region, which is all pointing to this point that we placed down here somewhere, quite low down, I think possibly a bit too low down, but it's just for illustration in this case. So if I switch off everything else, we're left with this kind of funny region, and one of the best ways to look at this region is with the wireframe mesh. So that's the mesh that it's extracted. We've from the blocky surface we've extracted this sort of smoothed out mesh, and we can start to measure some parameters off this mesh. What we're actually trying to do is imagine strands of muscle overlaid along this edge. But one thing I wanted to particularly bring out here was this idea that we're interested in the curvature across that skull, and we can see that there's obviously a marked break in the way that the skull of wombats actually seems to go. So that's kind of one of the things that we're interested in. We're interested in how the muscle wraps over this sharp break, and one of the ideas in the literature is that around this break there's going to be quite a sort of change of impact, and there will be a much greater pressure inwards of the muscle, rather than if we just selected this region and applied a sort of uniform load across it. What we're supposing is that there's going to be a much larger impact of the muscle around here, and because the muscle tends to get thicker as it goes along, imagining that strands are attached to each of these points, then there will also be an impact along the sort of leading edge towards our point. So that just kind of illustrates what's going on. I'll switch now to the fox skull model, because that's a whole lot easier to it doesn't have this strange artifact in on the teeth. So I'll just pause for a second. Okay, so if you have your release bundle directory somewhere, kind of like here, you should have something relating to the skull model, which contains our fox skull data. So if you all I've done here is switch to this directory, and I've run ParaView again. So if I maximize that and I go ahead and load this model, okay, using the standard VOX-FE tools, and while that's loading, I made an image earlier of what we're actually trying to aim for. So this is what we're actually trying to aim for here. I just zoom in a little bit. We're trying to load the model and to place boundary conditions rather that are fixed with a minimum kind of number of conditions, really. So we want one condition that constrains a point altogether. So we have a point sort of here on the skull which is constrained in all three axes. We have a point on the other side which is constrained in two axes, and it is we're allowing the skull to sort of move from side to side here as we place loads on it. So all the points, the rest of the points will be free to move, but this one will only be free to move in a kind of sideways direction. And we're going to place a final boundary condition which will fix the model sufficiently that the solution will be possible just in the sort of up and down plane, so that this point can't move in the up and down, but it can move kind of forwards or sideways. And then we're going to, like we did with the wombat, we're going to try and place a sort of muscle wrapping condition around the back of the skull, which is how we're going to load the model. So this is about fixing the model sufficiently that it's constrained without being over constrained, but we're going to apply some condition, the actual loading condition onto the skull. So if I drop out of this, hopefully our fox model's loaded, and we'll just have a little look round. Okay, so that's our fox skull model. The resolution is 0.2 of a millimeter, so it's fairly fine, but it's actually missing quite a few the finer details inside. So some of the fine trabeculae have been lost, and if I were to take a slice through this model, you would see that. But this is the purpose of this is just to try and examine this external loading model and how to set boundary conditions in a kind of fairly reasonable, quick way. So we're going to place our muscle wrapping condition on here, and you can see that it's a fairly sort of smooth, spherical kind of model. So actually this model doesn't exhibit a lot of changes of curvature, which is one reason I wanted to show you the wombat skull. But okay, so when it comes to setting boundary conditions, you've kind of got that many points here that it's kind of hard to choose from. So the best way that I've found of trying to do this is to actually select a few points roughly in the region that you actually want. So let's say this is the point that we want to fix in all three axes. We'll select a few points there, and you can see it's selected quite a few. So and we'll zoom in on. So I'll use right click and drag towards me to do that, and then if I use a middle click and drag, that pans. So right click and drag again, and and now we're in here. So I might now I'm in a position I know where I am working to. So I will try and say choose a point just here. So if I use the selection button and just try to click around that corner, then all being well, it should just select that point. Yeah. So any point there would do really. We're just trying to align the model with the axes, so that in this case, we're on the other side we're going to be constraining that only that axis can move. But now we've managed to choose our point where we kind of want to. So I'm going to place a boundary condition using this button, and I forgot to extract, so I need to do that first. Let's extract, and then I can place this boundary condition. So here we are, nodal constraint, and in X, Y and Z. If I apply that, we'll get the little icon that tells us where we're going. If I zoom out a little bit, just wait for that to finish rendering, you can see that the icon is really very small for that glyph. So I'm going to set that to about 5. Make it much more decently visible. This offset step really is a multiplier. So if I change this offset, it will be 0.4 by 0.1. So it's not going to actually move very much. So if I change this offset to 1, and then maybe to about that should. So it's moving moving the glyph downwards a little. So it's making it much more visible for us. So we've selected a point here, and the 3 triangles in this boundary condition glyph are showing us how that's fixed. So we now want to choose a point somewhere on the other side, which is more or less in the same axis. So I guess we want to be kind of on this tooth here, and follow the same sort of process. Right, that should do it. If I now click some points along that tooth to select, and then as before, I'll move that, pan that right into the middle, and then zoom right in. Pan and zoom again. That's just because you know, once you're in this close, it's kind of difficult to see what you're looking at. And a little bit more, and so I'm just going to try and select that point, and all being well, I've managed to select 2 points. Zoom a little more. Okay, repeat that again, just click and select that one. And right, well, we've got one of them anyway, which is just what we wanted. So if I push that out again, so you can see what we're trying to do is to choose across that axis really. So we're going to allow this model to be kind of free along this axis, but we can constrain it kind of forwards and up and down. So if I select the extract button, so that I'm applying it just to that point, choose our boundary condition button, and a nodal constraint. So as I say, we want to make it free to move in the Y, but fix it in the other 2 axes. So so we fix it in the X and the Z. Again, I'll change these glyphs symbols to something a bit more appropriate to this size, and we know that bringing it down seems to work quite well. So if I apply, then we should get those conditions mapped to that particular point, and that's pretty much across that axis. So and a third condition, because well, conceptually the model is still kind of free to rotate about that axis. We want to place a third point, let's say on this tooth, which is sort of pretty near to a kind of Z direction in this model. So I'll follow the same procedure. If I choose a few points on there, and that just helps me to kind of select them later on. If I then rotate and pan my model, zoom right in, and this point looks good, so I'll try and select one of those points. Let's say this one. Okay, didn't get any. I'll try and choose that corner. Yep. Well, I got this corner, but that's fine. So let's just zoom back out again. Yep, that's okay. So now we want to just stop our model from stop that point from moving upwards. So bring it back into this space. So we want to constrain this point in the up and down sense, which happens to be X in this case. So if I extract that point and apply, and then add a boundary condition to that point in that X-axis, and change these to match the others, and just bring it down a little bit. Okay, so and I'll use this highlight button to give those symbols a bit more colour. So we've now constrained the model from moving quite nicely. So it's not over constrained, but it's not under constrained, and it's not. It should solve as well quite well. So now we've got that done, and we want to choose our muscle wrapping region. But a nice thing to do at this stage would be to save the state of the model, so we don't have to go through all this procedure of recreating all these points and zooming in and stuff. So a nice thing to do is now to save the state, and you can see this is one that I did earlier, but we'll just call it 1, and that basically runs through all. If you then use load state for that, it will run through all the steps. If we do load state and load that model, it will run through all the steps that we've just done to recreate these boundary conditions. It will keep them for us. So now we want to move on to applying this sort of muscle loading condition. I used the spreadsheet function by selecting some points on a tooth. Obviously, if you've got a whole model that where you've actually got a lower jawbone as well, you'd want to import that using the sort of keep components function, which is in the original thing. If you'd happened to have got the lower skull in your image data, you'd want to click that so that you kept your lower jaw model, and you could actually choose a particular point on it. But as it happens, I've just chosen a point here, as I say, using the spreadsheet function, and something like that. So if I now choose some points here, and that it does take a little while running on this laptop to do this, I'm afraid, but that's how it is. And then if it comes back here. If I click that button, those will be the points in that region. So I've decided that there's a point that we would want somewhere about 50, 20 something, and about 80, being a little bit further down here. So that's how I've managed to choose my target point. And I think that possibly the muscle on this model would actually be distributed all the way around. But I'm just going to choose a fairly small region if it comes back from rendering, just to illustrate the way that this muscle wrapping function actually is applied a bit more fully. So again, if we like with the wombat skull, I choose this sort of little hand mapping region, select points with a polygon, it says, and then I just choose some region around here. I think in reality it would probably, this region would extend all the way around, but for the purposes of this exercise, I'll just choose this slightly smaller region, and we'll find that like what happened before, that it's a bit difficult to tell how many points have been selected, but what I've found is that it's better to kind of move the model and click this again, and then use the control button to add points. So if you take a slightly different perspective like this and paint more or less over the same area, usually that fills in some of the points that you would have otherwise have missed, and that improves the way that the mesh appears at the end. If you get a very bad mesh, it's well worth repainting your region and then doing it from a number of different angles, and making sure that you haven't got any kind of extra points kind of outlying. So I mean, if you happen to have chosen this ridge, say by selecting from here, it would be easy to choose points on this ridge. And if there's a big gap between the sort of main region and then some other points, you'll get a really bad mesh on that edge. So the quality of your selection really is important here. But I'm going to stop there for now, just for this tutorial, and I'll extract using that button. And again, well worth just checking that there's a pretty good spread of points. Obviously that's from the voxel mesh, so it is going to be a bit irregular, but you do want a kind of nice distribution of points, or otherwise the algorithm is going to fail quite badly. And you can see that maybe it's a bit patchy in here, but I'm going to try from this anyway, and you can see that there are kind of ridges here. So I think if I were doing this more fully, I would want to try and fill in more points here, which in this case would mean really starting again. But I've extracted those points, so now I'm going to try the muscle wrapping condition anyway. So the ordinary boundary condition function is here. This is the muscle wrapping loading condition, and let's suppose that I'm going to have a total tangential force, which is a force sort of acting at the surface of the model along in the direction of your target point. So if say from a point here, we would assume that the muscle might wrap around in a bit of a curve and then maybe come down towards this jaw point that you've selected, and I'm saying that the total force in that direction is going to be, let's say, 10 newtons. The scaling here is an interesting parameter. We're still trying to work this out, really. This feature is really kind of new and a little bit experimental, but this would very much depend upon what units you were working in, that you would probably need to scale the forces to be appropriate, because what we're trying to do is to say, okay, well, we assume that the tangential forces sum up to 10. Now let's try and use this curvature and the sort of muscle length parameters to work out what the inward force would be. And the literature is a little bit vague about this, so I've allowed that there is a parameter in here, and I'm just going to set this to 0.1. It could be that in your case that you would rather choose something else. It's rather arbitrary, but that is how the situation is really. The krigging is how we take the this sort of very coarse mesh with its bits of holes and things in it, and it is very lumpy because it's come from this kind of quite ridged, blocky mesh underneath. But these parameters are, in general, are pretty good parameters. So it's about trying to smooth this blocky mesh into a smooth surface mesh. The krigging parameters, generally speaking, you're not going to want to change these much. This next panel is about uses the set of points that the krigging generates to estimate normals and curvature, and these are normally pretty good parameters for most purposes, but the one you're probably going to have to change is this, and what we suggest, if you look at the bubble that comes up, is about 5 times the voxel size, and because this is 0.2 of a millimeter mesh, 1 actually is 5 times the voxel size, so I'm going to leave that as it is. There, the target point, as I said, I've worked out beforehand using a spreadsheet function as a bit of a guess. So 50, 26, 80 to be quite reasonable parameters. And the other parameter that you probably want to change, what we find is that the mesh that this will generate will be quite coarse along this edge if you leave this parameter at something like 10, because what that's saying is that 10 is fine as a kind of gap size. In actual fact, you want to set this to sort of 2 or 3 times the voxel size, so that the gaps along this edge, it's going to generate these sort of strands off towards this target point, and you're not going to want that to be much bigger than a let's say twice the voxel size. So 10 here would be a huge gap, and it would leave very widely spaced strands, which would influence how the length measurements are influenced over the surface. So a good rule of thumb measurement here would be sort of, let's say, 3 times the voxel size, or 2 or 3 times the voxel size. I'm going to say, okay, 0.5 seems quite a reasonable value, and then that's all good to go. We click apply, and it will take a little while to run this because it's working sort of path lengths and these tangents and normals for every point in the mesh, but it's not too bad. As you can see, it's finished working now. First of all, the thing to look at is how does this actually kind of make sense. It looks as if our patch is too small because of the way that this this is trying to represent how the muscle would sort of come off the edge of the skull. You know, it looks like this would be a better edge really, where the muscle sort of ceases to be attached to the skull. So that would be the first thing to kind of criticize here. If I switch off most of this other stuff so we can just see this patch that we've just generated, and because it is quite a fine mesh, it does very often come out a little bit dark, and it's better to switch this to a sort of wireframe view. And it's color mapped here using distance, which is distance from our target point. So you can see the blue is very close, obviously, and these points are much further away. So that a muscle that was connected here, that was running all the way down here, would lead to quite a long length of muscle, and we'll be applying quite a large kind of edge force around our patch. If I look at some of the other parameters, this is the remodeling thing that we saw. So what that choosing that value of 0.5, which was down here, has done is taken out some of these long edges, where, as I said, this would create some strands that are very far apart, and what it's done is it's created strands inside here, and you can see that even this looks quite far apart really, but it's not too bad. So where you can see these edges, it's taken out strands and added new ones in between to try and make this a more even edge. These bright spots are all the points at which the path length algorithm has worked out that paths all start. So if we consider this this point to be a target, then these are all kind of source points where, as it were, a muscle kind of starts. You expect them to be oriented around the edge actually, but what happens is that there are favoured paths, and so there are quite a lot of these source points inside the object. This is not really a critical factor. It's just informing you how this algorithm is working really. So something else to look at would be the curvature, and as I said, because it's quite a smooth spherical kind of skull, there's not actually a whole lot of curvature going on. You can see that in cross section it's actually moving, but it's actually quite a consistent sort of curvature, so there isn't a great wrapping effect on this skull, except towards the edges where obviously some slight error creeps in really, but in between times the curvature is really pretty constant for this skull. I think if we'd chosen points nearer to the ridges, obviously we'd get more of an interesting effect, but that just shows that most of the curvature is fairly sort of constant here in between kind of 0.1 and 0.2, which is kind of indicating that a sort of circle fit for, let's say, 1 in 10, or at 0.2 kind of 1 in 5 circle radius, so a radius of 10 or a radius of 5, but it's a fairly constant feature in this case, so it isn't going to be applying a great deal of effect to the actual curvature. Something else then that we might want to look at would be how this muscle accumulates across that patch, and that's what this visualization is trying to tell us. It's suggesting that the paths kind of accumulate along certain tracks, and that's where this kind of edge refinement gets even more important. And this model really is trying to tell us that the muscle sort of seems to collect in these fibers, so there's a certain sort of weight of muscle along these favoured paths, which is very large, and we'll see how large in a minute when I look at the way that the forces interact. So the best way to kind of look at the way that that muscle force is attached, actually acts rather, is using glyphs applied to this surface. And if I then switch this, so if I apply a glyph, because I've used it, the glyph filter is here, but if you can't find it, you have to go to the alphabetical thing and look down here. You'll find it somewhere down here. So this will apply a glyph filter to our object, our selected object, which was this, and what it's looking for really is any kind of vector quantity that's in our color map region. So it picks out all the vector sort of 3-component arrays that are in our data. And what we've done, we've used this path information, and we've used the normal data to calculate what this sort of inward force is. So if I look at the path vectors, this usually tries to estimate a reasonable size of the glyph. So we'll kind of go with that first, and then we'll probably have to use this to edit it and apply this. So it'll probably come up with lots of large glyphs, but actually it's not bad. It's kind of showing this how it's favoured these certain paths. If we were to increase this, you would see how these paths vectors are kind of made up across the whole model, but unfortunately, because it varies and we're using it to accumulate this information, it kind of gets very hard to see exactly what's going on. We can change this parameter here to see, but that's the path vector. If we want to look at what the normal data looks like, I think you'll see that it kind of points upwards, and point 1 was really a little bit too small because the constancy, you know, there's no accumulation. It's just that they're just unit vectors. So a factor of 1 would probably be okay, but I think I tried 2 is probably a better bet. So those are all the sort of normals that the algorithm has calculated for the points across that surface. You can see that it's sort of, they're basically following the wavy path of that surface. And the other thing we can look at the same sort of scale are the tangents, and they are tangent to the surface, but also in the direction that this muscle is trying to pull towards. So they are kind of towards this target point that we've set up. So it's totally dependent upon what that is. And the thing that we're really trying to get to in all this is what the resultant vector would be between the normals and the tangents. So that's this resultant force here, and this will be very much smaller because it's scaled down, or otherwise it just gets very, very large. So and remember, I've used this scale factor anyway, so we probably want to scale this up a little bit more. Probably 100 will even be too small. So 1000, yeah. So now that's probably gone a little bit large, but it does show what the effect of this is. So we're now getting this increasing force over towards this edge, as the model predicts that the weight of muscle is going to increase along this edge towards this target point, and so it will be greatest along this edge, which is exactly what we can see. But also because of the way that these paths are being favoured along the muscle, you will see very large resultants occurring. So along this edge and along these favoured paths, and really it will have to be up to some future work to how best to scale these forces. So I'd like to just finish off really by saying that you would export these this boundary condition, all these boundary conditions, in the way that you would that I showed in an earlier tutorial. I've switched the other boundary conditions off, so if I switch them back on again, just run through this export routine. This is kind of the model as we've got it, with our constraints along here, with our muscle wrapping condition as shown, and we would use this export button. So this button is supposed to be writing out your constraint and loading conditions for your solution file. So the way that you would export those conditions is to click that button, and the input model is always the first thing here anyway, but it's needed to work out what the mesh size is and some of the other properties. And then the boundary conditions that you want to export, well, you just use Control and left click to select them. So we'd want to do Control left click on all these things, and the last one here would be our muscle wrapping. Object. Okay, so we have our object selected and the change input dialog is always the first object. Then we need to choose our boundary conditions, which will be the 3 points that we placed and this muscle wrapping condition. So we control click, keep your finger on control, and just check that everything's still selected. So that's the 4 conditions, and you just click OK and apply. And all being well, that should then create a constraints file, which, because it's in this directory, will contain the data as we saw. So we constrained 1 point over the 3 axis, another over the 2 axis, and then this final one over the just 1 axis, and then this is the forces that our output across that patch into our model, and which we can feed straight into our solver. So that concludes this tutorial. Thank you.